All right, so we were talking about the matrix tree theorem, which was a formula for the number of spanning trees of a graph. So we said that if a graph is connected, then the number of spanning trees of the graph can be obtained in two equivalent ways from linear algebra from the matrix called the Laplacian. So the Laplacian of the graph is a V by V matrix, where V is the set of vertices, and the entry I comma j is going to be, if you're off the diagonal, if I and j are different vertices, then you put minus the number of edges between I and j. And on the diagonal, where I is equal to j, you put the degree of corresponding vertex. Okay? And so we saw that we talked about how this is a singular matrix. The determinant is 0. But then what we did is that we took a principal cofactor. So we erased row I, column I, and we took that determinant, and we proved that that determinant is equal to the number of spanning trees of the graph. And there's another statement which I said but I didn't prove, which is that if you look at the eigenvalues of the Laplacian, lambda 1 up to lambda n, and we said that one of them is 0 because this is a singular matrix. If you take the product of the other eigenvalues and you divide it by n, you also get the number of spanning trees. Okay, so this is equal to this. And I was realizing, as I was preparing class today, that I forgot to prove this last time. But anyways, it's proven. So we proved this. We proved that this is equal to this, but I didn't prove this linear algebra fact from here to here. But you can see the proof in the notes. Okay, it's there. And so what I want to do today is apply this theorem a little bit more. Last time we used it to give another proof that the number of trees on n vertices that are labeled is n to the n minus 2. But now I want to use it to prove something that we didn't know yet. And so to do that, let's see. Let's go over here and talk about cubes. Okay. So the n cube Cn has 2 to the n vertices. Each one is an n tuple where ai is 0 or 1. And 2 vertices are adjacent if and only if they differ in exactly one coordinate. Okay. So maybe the most familiar cube for you is n equals 3. So, but let's start with n equals 1, or even n equals 0. Let's start with n equals 1. 0 is too boring. So C1 has 2 vertices corresponding to the number 0 and the number 1. Okay. C2 has 4 vertices, and I'm going to color code this because this is going to play an important role. So one way of getting the 2 cube, which is the square from C1, is just to take 2 copies of C1 and join them to each other. And it's like saying this is the 0 copy. So this is the 1 cube. This is also the 1 cube, and I put a copy at 0 and a copy at 1. Okay. Let's go to the next one. So this is what we are used to calling the cube. Okay. And so what I do is that I draw 2 copies of C2. Then I kind of join them to each other. Okay, so
Shouldn't it be black? Trying to do 2 copies of C2.
So, right, so this is one copy of C2, and I'm going to do another copy of C2. I'm going to put it, let's say, over here. And then I'm going to join them by a new direction. Like this. So I don't know if you've ever drawn a 4-dimensional cube, but if you haven't, you should. Maybe I won't do it in front of you so that I don't spoil the fun, but this is what you do. You do one of these, you do another one, you draw another one next to it, and then you kind of connect the corresponding vertices. These are the n cubes. Now this is, okay, so we're talking about graphs here, and so really here I'm only concerned with the graph of the 1 cube, the 2 cube, the 3 cube, but of course these are polytopes, and they live in, Cn lives in n dimensions, but that's not going to be important to us. We're only going to pay attention to the graph. Okay? So I am interested in proving the following theorem. The number of spanning trees of the n cube is equal to the following number, 2 to the n minus 1 times 2 to the, 1 to the n choose 1, 2 to the n choose 2, 3 to the n choose 3, dot, 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 up to, how far should I go, I guess, n to the n choose n. This is the number of spanning trees of the n-dimensional cube. Beautiful formula, right? Very intriguing. And one thing that's very, very intriguing about this is that nobody knows a combinatorial proof. So here's an open problem. If anybody's interested, open problem. No one knows how to do this, find a combinatorial proof. Which is very strange because the answer looks very combinatorial, right? But no one really knows how to do it, yeah?
Is it ever possible to prove that there is no combinatorial proof? Like, to prevent people from wasting their time?
So the question is it possible to prove that there is no combinatorial proof? I would say probably not. Yeah, I don't have a great answer to that question, but I've never seen a statement like this.
How is it proved? Like what? I mean, algebraically or?
So how do we prove this, right? That's the question. How do we prove this? Well, that's what we're gonna do. And you see the good thing about this. I mean, we think, okay, this asks for a combinatorial proof because it's a product of simple numbers, right? So it looks like you're making a bunch of decisions and it all looks very simple. But here we have something that's also a product of numbers, right? And we have a bunch of numbers, right? And so maybe what we should do is show that all of those things we're multiplying are just eigenvalues of some matrix, right? Does this make sense? Well, what is n in this case? It's too bad that I use the same letter, but n is the number of vertices here, right? What's the number of vertices of the n cube? It's 2 to the n, right? So what's the number of eigenvalues? It's 2 to the n minus 1. Right? I'm supposed to divide 1 over 2 to the n. Okay, here I have something involving 2 to the something. And then I'm supposed to multiply 2 to the n minus 1 numbers. How many numbers do I have here? N choose 1 plus n choose 2 plus n choose 3, etc. That's 2 to the n minus 1. So this should work out. It looks like these should be the eigenvalues of these graphs. At least something like that should be true. So that's what we're going to show. Actually, before I continue, let me mention that there's a very, very interesting generalization of this that is also open, and this is one of the projects. Higher dimensional generalization. What is wrong? So I think that's a very interesting problem, and in that case, not only is there no combinatorial proof, there is no proof at all. So there's a conjecture, and it looks very similar to this, and there's no proof available for a higher dimensional version of this statement. So I think that's very interesting.
What do you mean higher dimensional?
It would take me a while to explain to you what I mean by higher dimensional, and I think just if you're interested, I'm happy to tell you. If you want to look at it in the project, or I can tell you afterwards in office hours. But that would kind of take us to a... The point is that there's a theory of higher dimensional spanning trees that live, that are not trees, that are not graphs, they're higher dimensional things. And so this is about that. Okay, so how are we going to prove this? So maybe... Okay, so what I'm going to do is this. Here's the definition. If I have two graphs, and maybe I'm going to try to distinguish their colors. So you should be thinking of something like what I'm doing here. And then the product graph. Okay, so these are graphs. We are going to define the product graph so this is going to be the graph on pairs of a black vertex and a blue vertex and edges so whenever I have a black edge from, let's say, U1 to B1, so then that's going to give me an edge U1, B2 from U1, B2 to B1, B2. And whenever I have a black edge, I get a bunch of copies of that black edge in my product. And whenever I have a blue edge, that creates so whenever I have a blue edge, that also gives me an edge in the product. Okay. So basically, I do what I'm doing in that case. Okay. So every black edge gives me a bunch of edges in the product. Every blue edge gives me a bunch of edges in the product. I think this is the clearest if I do an example. So, for example, what is, let's say, this graph times this graph. It's going to be easier if I draw it longer. So basically, I'm going to get, I put a copy of this graph on each one of these vertices. Okay, so I get this thing here. And then I join the corresponding vertices. So that's the product graph. And so the reason that I bring this up is that C2 is a black edge times a red edge, right? And C3 is a black edge times a red edge times a green edge. And in general, Cn is just C1 times C1 times C1 to death. So this is n times. Okay. And if I want to find the eigenvalues of Cn, it would be very useful if I know what the eigenvalues of a product are. And it turns out that that's very nice. So here's a proposition that if the Laplacian of G1 has eigenvalues lambda 1 up to lambda n, and the Laplacian of G2, maybe I'm going to try to keep this color coded and see if I don't get sick of it, has eigenvalues mu1 up to mu m, then I'm already sick of the colors. The Laplacian of G1, G2 has eigenvalues what? What would you hope? Maybe you multiply them, maybe you add them, maybe you do something, but it should be some kind of combination of these. Now, first of all, how many eigenvalues should I have? Well, if this guy has m vertices and this guy has n vertices, then this guy has m times n vertices. So I need m times n eigenvalues. And it turns out they're just lambda I plus mu j. For 1 less than or equal to I less than or equal to n, 1 less than or equal to j less than or equal to. Okay? So, okay, I'm gonna erase this beautiful formula to prove this fact. So let me take one eigenvalue here, lambda, an eigenvalue here, mu, and let me show that lambda plus mu is an eigenvalue here. So to do that, let R be an eigenvector of L of G1 for eigenvalue lambda, and S be an eigenvector for the Laplacian of G2 for eigenvalue mu. Okay? And now I need to show that lambda plus m is an eigenvalue for these guys. So what I'm going to do is cook up an eigenvector. So the way I'm going to do that is that I'm going to define T to be, and by the way, how long should that eigenvector be? Well, remember that this guy has length m times n. And so this should be a vector with m times n entries. And the n times n entries are going to be Ri times Sj. I guess I call this n and I call this m. Okay? So this is a vector of the right length, and I claim that this is an eigenvector for the product graph for the eigenvalue lambda plus mu. Okay? So how am I going to do this? Well, first of all, what does it mean for this to be true? So if this is an eigenvector, then the Laplacian times the vector is equal to lambda times the vector. Right? So what does this mean? This means that I should multiply this vector by that matrix. Right? So what do I get when I look at the ith entry? Well, on the right hand side, I get lambda times ri, right? That's the ith coordinate of this. To get the ith coordinate of this, I should multiply. I should carry out this multiplication, right? And so what do I get? I get the degree of I times ri minus the sum over over the edges like that of rj. This is what I get when I multiply the Laplacian by my vector r and I look at the ith coordinate. Okay. So this should be true for all I. Okay. So these are some linear relations between the ri's that tell me that this is an eigenvector, and similarly for s, so this is going to be mu s, then I get that the degree of j times s. See if I should just use. I was planning on keeping the color coding, but I think that's going to be a nightmare. So what we're going to do is that we're going to remember that lowercase vertices are in G1 and uppercase vertices are in G2. Okay? So now I'm going to take some entry between 1 and n capital. Okay? And so then what I get here is the same thing, but with capital letters. Okay. And maybe I'll also switch this one to a capital letter so that I remember that. Okay? And so now what I have to do is carry out the same computation in the product. So I need to find the I entry of Laplacian of G1 times G2 times T is equal to kind of the same thing, but now for the product graph. Okay? So what do I get? I get the degree of the vertex I comma I in the product graph times T sub I minus summing over the neighbors of this vertex. Okay. Now, what are the neighbors of this vertex? Well, there's two kinds of neighbors. There's black neighbors and there's blue neighbors. Okay. So the neighbors are either obtained by changing the first coordinate or by changing the second coordinate. These are the two kinds of neighbors that the vertex I in the product graph has. Okay, so here I should do T Gi, Ji minus T of Ij. Okay? Now, what is this? What is the degree of II? Well, again, think about it. So if you have a vertex in the product graph, how many edges come out of there? Well, the black edges and the blue edges. And there's degrees of I black edges and degree of capital I blue edges. Now, by definition, Tii is Ri as capital I. And then I get minus sum Now, I is a neighbor of ji when I is a neighbor of j. G1. Okay? And tji is rj si. Right? And similarly, now I sum over the neighbors j of I, and I get here ra as capital G. Okay? Now, the good thing about this is that now, you see in this summation, I can pull out this S capital I. This is a constant in this summation. So I'm going to pull it out. So I get Si over here. And here I can pull out the Ri, right? That's a constant in this summation, so I'm going to pull it out. So I get minus Ri times this. Okay? So let's go over here. So the thing is that now, what happens when you look at this term and this term multiplied by this term? You get, let's put all that together. So we get capital Si times degree of I, Ri minus sum of over the neighbors of I of Rj, okay? And then when I join the other stuff, I get plus Ri times the degree of j, sorry, degree of capital I, sorry, minus sum over neighbors of capital I. Oh, I forgot the Si minus sum Sj. I get this, right? Now, how much is this? Well, this is exactly what I have right here. Right? So this is equal to Si times lambda Ri, and then on the other one I get this, right? Plus Ri times mu as capital I. This is equal to this. And so what I get is lambda plus mu times Ri as capital I, which is the I entry of lambda plus mu. I mean, this Ri Si is the same thing as T I. Right? And so what this says is that this is precisely lambda plus m times my vector t, which is saying that this is an eigenvector. And the eigenvalue is lambda plus mu. Okay. So this is the end of the proof. Well, this is almost the end of the proof. The thing is, okay, so what did I just prove? I proved that if lambda is an eigenvalue of my first graph, and mu is an eigenvalue of my second graph, then their sum is an eigenvalue of the paragraph. And if these guys are different from each other and these guys are different from each other, I'm going to be done. But there are issues when if you remember when eigenvalues are repeated, then you need to worry about whether the eigenvectors are linearly independent or not, and whether they're kind of eigenvectors or generalized eigenvectors. And so there's kind of some subtle linear algebra issues that arise, but that all work out. Okay, so this is maybe a proof sketch, but this is essentially all there is to it. Okay, and that proves this proposition. Okay. Cool. And this proposition is great for us because now it's going to be very easy to find the eigenvalues of the cubes. So what are the eigenvalues of the Laplacian of C1? Well, the Laplacian of C1 looks like, it's a very boring graph, right? It's just this graph. It has two vertices, each one has degree 1 and they're connected to each other. So what are the eigenvalues of this thing? One of them is 0 because one of them is always 0, and the other one is 2 for several reasons, one of which is that the trace of this is 2. So the eigenvalues are 0 and 2. Okay? So what are the eigenvalues of C2? Well, given that C2 is C1 times C1, what I'm supposed to do is add one of these to one of these in every possible way. Right? So 0 plus 0, 0 plus 2, 2 plus 0, or 2 plus 2. So they're 0, 2, 2, and 4. Now what are the eigenvalues of the next one, L of C3? Well, C3 is the product of C2 with an edge. So I'm supposed to take one of these guys and add them to one of these guys in every possible way. So what do I get? I either get 0 plus 0 plus 0, or I get 0 plus 0 plus 2, or 0 plus 2 plus 0, or 2 plus 0 plus 0, 0 plus 0 plus 2, 0 plus 2 plus 0, 2 plus 0 plus 0, or I can get 0 plus 2 plus 2, 2 plus 0 plus 2, or 2 plus 2 plus 0, or I can get 2 plus 2 plus 2. And in general, actually, if you want the L of a product of things, then you just kind of look at all the ways of adding n of these guys. Right? And so that's why I'm getting here all the ways of adding zeros and 2s. There's 2 to the n such ways. And you see what I get is, 1, 0, n choose 1, 2s, n choose 2, 4s, etc. Okay? So the eigenvalues of Cn are 1, 0, a bunch of 2s, n choose 1 times, a bunch of 4s, n choose 2 times, up until the biggest one, which is 2n, which appears only once, which is n choose n times. Okay. So this is either by hand waving, or you can prove it by induction also. But those are the eigenvalues of the cube, and then that means that by the matrix tree theorem, the number of spanning trees of the cube Cn is, I'm supposed to divide by the number of vertices, which is 1 over 2 to the n, and just multiply all of these numbers. Right? So I get 2 to the n choose 1, 4 to the n choose 2, 6 to the n choose 3, etc. up until 2n to the n choose 1. So with a very small amount of work, you can get this to look like the other formula. So that's the proof. Okay. I like this proof a lot, but it really doesn't explain. I mean, I guess all I'm saying is that I do wish that there was a bijective proof, because the answer is very simple. So I don't know, maybe one of you can do it. That would be awesome. But you see how we're starting to use more interesting linear algebra to get results. Okay, and basically, whenever you try to do this for more intricate graphs, this is especially bound to work when your graph has a nice combinatorial structure that allows you to prove things about the eigenvalues. Right? Complete graph, or the cube, or these kinds of graphs. This is a very useful method for computing number of spanning trees. Okay. Any questions about that before we continue?
Why do you like this proof again? Is it just because of the answer or the linear algebra?
You don't like it? I think it's beautiful.
I didn't say I didn't like it. I asked why you liked it.
Why do I like it? Because I think it's beautiful. Because I think, yeah, I don't know. I mean, one thing that I should say is also that if you pick a random square matrix and you ask what the eigenvalues are, you've done this before. You get awful numbers, right? Unless it's a question that was designed in a linear algebra book where by luck you get the, not by luck, by very careful construction, in linear algebra books they make the eigenvalues be integers, but any matrix, if you just try it, you're going to get awful eigenvalues. And I think it's pretty remarkable that when you have this combinatorial structure backing you up, when you have this kind of matrix that has combinatorial structure, it is not so rare in combinatorics to have matrices that have integer eigenvalues. But it's still very remarkable. We still get very happy when it happens, but it does happen with some frequency in combinatorics. And then for free you get this beautiful formula. So that's why I like it. Okay. So now what I want to do is talk about another matrix tree theorem, but now it's going to be for directed graphs. Okay. And before I'm able to state this, actually, I need to make some preliminary comments. So what's a directed graph? It's just a graph where every edge has an orientation, right? So let's take a directed graph. These things are often called digraphs. Okay. So it's something like this. It's like a graph, but now each edge has some orientation. Okay. An Eulerian walk is a closed walk in the graph that uses each edge exactly once. Okay, this, I don't know about here in the US, but in Colombia, this is how people learn about Eulerian walks. Is this puzzle familiar to you guys? So the puzzle is, how do you draw this without lifting the pen from the paper and without retracing anything? Okay. And what you learn is that, you know, if you look at the degree of each vertex, right? This guy has degree 3, this guy has degree 3, this guy has degree 4, 4, and 2. What's the difference between even and odd degree? If it, you know, I mean, the point is this. The point is that if you want to draw this, you're forced to start here and end here. Why? Because you leave, okay? Now, all the other vertices that are not the ending or the starting point, you have to enter and exit. Okay? Enter, exit, enter, exit. And if you don't finish or start there, that means you have to enter and exit an even number of times. Right? Which means that these guys could not be intermediate vectors. They have vertices, they have to be the beginning and the ending. Okay? And then once you know that, it's actually really easy. You just do it and you almost can't. I mean, I could even do it with my eyes closed, maybe. I don't know. You go like this, and you just... The contour is, oh, look, can you use the center or not? Well, you can use the center, why not? It also has... I'm just going to call this a vertex, and it has degree 4, that's fine. it's even. And you know, if I start, I'm probably not going to get stuck. I hope I'm nervous. Where did I start?
Go right. Go right.
Oh, no.
No, it's fine. Go right. On the bottom edge. The bottom edge.
Oh, yeah. See, doing it in front of you guys is always kind of... I like this saying a lot. I wrote this in on one YouTube comment. I don't know if you saw. It's this saying that boards are made of kryptonite and you just lose all your thinking powers when you're here. And especially when you're being filmed, I feel like I can't think in front of a camera. But anyway, really, like if you don't have a camera, if you're not doing this on the board, you just can't get stuck. It's a very easy thing to solve. Okay. So this is a similar problem, but for one thing, it's a closed walk. Okay, and what that means is that you're going around and around and around. So, or in other words, closed means that you start where you end. Okay. So here you cannot do a closed walk because of these two vertices. Okay. But for example, if you added this. Now everybody has even degree, and it's very easy to do a closed walk. Okay. Now here what we're talking about is a version of this where everything is directed. Okay. So maybe we'll look at the same graph, but now it's going to be a directed version of it. So and then what should I make sure of now? Well, the thing is that each vertex you want to enter it k times and you want to leave it k times. So you have to make sure that at every vertex you have k things going in and k going out. K in, k out. And as long as I do that, I don't know. So these two are like this, then I guess these two have to be like this. And in, out, out. In. I think here I'm satisfying that condition. Okay. And so here's a theorem. Okay. Yeah. So here's a theorem or proposition. This is too easy to be called a theorem. Proposition. D is Eulerian, meaning that it has an Eulerian walk. If and only if for each vertex the in degree equals the out degree. For all vertices. Okay. So this is how you know whether you have Eulerian walks or not. And let me very quickly give you a sketch of the proof. I wrote this in more detail on the notes, but I'm a little bit short on time for what I want to do, so maybe I'll just kind of draw a picture to indicate what happens here. So it's very clear that if it is Eulerian, then this condition holds, right? Because at every vertex you enter it and you exit it the same number of times. The trickier direction is to go from here to here. Okay. So let's assume that we have a graph where each in degree equals the out degree, and let's prove that it has an Eulerian. And what we're going to do is that we're just going to walk. Okay. So this proof is called just walk.
I have a question.
Yeah.
So the one that we drew on the red one, that one doesn't have Eulerian walk, right? Because it's not closed. But all the degrees are. Oh wait, never mind.
So the trouble with this is that it's not directed, right?
Yeah.
So maybe I don't want to erase it, but I want to like this. This is not what we're talking about. We're talking about a directed graph now. Okay. So everything comes with an orientation. So just walk. What do you do? You just start with you just pick a vertex and you start walking. Okay. Now, I guess the only thing is that if you want to be able to do this, the graph should be connected, right? Otherwise you can't possibly have an Eulerian walk. So let me say a connected graph C is Eulerian if and only if this happens. So what I'm going to do is just walk, okay? Pick an edge. Just walk. Now, because I entered it, that means I can exit it, right? Because if there's in degree at least 1, there's out degree at least 1. Again, because I entered it, I can exit it. Because I entered, I can exit. Because I entered, I can exit. Because I entered, I can exit. Maybe I hit something that I've already used, but still, because I entered it, I can exit it. Because here I have, I have two coming in, one going out, so there must be another way to go out. So you just keep going, you keep going. So why can I not do this forever? I mean, at some point this has to end because this is a finite graph and I'm only using edges that I haven't used. I'm not repeating edges. So how can this process get stuck? The only way that it can get stuck is if you hit the vertex that you started with. Because in that case, this vertex is in an out imbalance, and now by coming into it, you close the cycle, and now you could get stuck. Okay? So you say, okay, am I stuck? I'm stuck. Am I done or not? Maybe this is the whole graph, and if so, great. But maybe this is not the whole graph. Maybe I missed some stuff. So if I missed some stuff, because the graph is connected, that stuff must be reachable from what I drew here. Right? So there must be some vertex in my path that had an out edge that I didn't use. So let's take it and just start walking again. Walk, walk, maybe you walk in here, you walk out, walk, walk. How can I get stuck? Again, the only way I can get stuck is by hitting this vertex again. So I keep walking until I hit this vertex again. Okay? Now what's the point? The point is that if I can do a closed walk like this, and if I can do a closed walk like this, I can actually join them into one walk by starting at this vertex, doing the black stuff, and then doing the blue stuff. So this is now only just one walk, right? And it's bigger than the previous one. And so I ask, am I done? If you're done, great. If you're not done, repeat. And you just keep going, keep making it bigger, bigger, bigger. At some point, you have to get stuck, and the only way that you can get stuck is if you're done. So that's the proof. Okay? Now, okay, so it's not just walk and correct if necessary. Correct if necessary. Right, so, I mean, actually you could try this and get stuck, and you shouldn't be too ashamed of yourself, but you should just know that you can fix it, right? You can just keep going and correct your track according to this decision. Okay. So, now what I wanna remark is the following. With a bit more care, with a bit more advanced planning, to hit the whole graph, I get a much stronger statement. This is the main theorem that I want to discuss. Theorem. Let D be an Eulerian graph, Eulerian directed graph, right? On N. Okay? And choose any edge let V be the starting point of that edge. Okay? Now, let this be the number of Eulerian walks of D starting at E. Okay, the number of ways that you can traverse this graph starting with the edge E. Now you might say, this is kind of weird, why starting with E? If it's a closed walk, it doesn't really matter where you start, right? You have to hit every edge exactly once. And so, really it's not so important. I mean, the point is that this is independent of E. Because closed trails, you can start wherever you want and just run around it, and you're going to get the same thing. Okay, now let's let tau of D comma B be the number of oriented spanning trees of D rooted at B. So let's talk about what that means. Actually, maybe instead of talking about what that means, let me just do an example. So let's say that I want a tree rooted here. Spanning tree rooted here. So that means that it has to be a spanning tree such that all edges point towards B. So B is the root and everybody else points towards B. So let's see if I can accomplish that. I can do that, for example, by doing this. You see, for example, if I want to go from here to here, I can't take the straight path because that doesn't point towards B. So I have to put this in my tree. Okay. I guess I can connect like this, and like this, and like this. So this is an oriented spanning tree rooted at V. All edges point towards V. Did I get that right? In this example, you see, here's B, and everybody points towards B in this tree. And I did hit every vertex, right? Mm-hmm. Yeah. Yeah, that's true. Yeah.
I'm gonna hold on my question.
You can pause the video and look at it longer, and you'll see that this is oriented.
I totally agree with that, but I have a question, but I want to think about it first.
Okay. Okay, so here's the remarkable theorem, is that actually these two numbers are almost the same. The number of Eulerian, I mean, they're not almost the same, but they're very closely related. The number of Eulerian walks is the number of spanning trees times the product from I equals 1 to n of the out degree of vertex I minus 1 factorial. Yeah?
I got a different question.
Yes.
Every oriented spanning tree, for that particular graph, every oriented spanning tree will not have those only those two edges that point directly away from V. Like every oriented spanning tree won't include either of those two edges that point directly away from V, but every other possible edge could be in a spanning tree of V, oriented spanning tree.
So you're saying that in an oriented spanning tree, I'm never going to use this edge. That's true.
Okay. And the other one.
And I'm never going to use this edge. And you're asking what about the other ones, and the answer is I don't know. Oriented spanning trees are a little bit trickier than spanning trees because sometimes the orientation can get in the way of accomplishing
So
this.
all edges that point to V must be able to get to V by a sequence of other edges along its path, so to speak.
Yeah. Yep.
If that the diagonal blue line that you have, if we had changed that to be the vertical left-hand side line, would that still be an oriented spanning tree? Because from that top right vertex or top left vertex, yeah. So if that diagonal.
So if this diagonal went to here, this would not be an oriented spanning tree
right.
because
Okay.
because this edge would be pointing away from me.
Got it.
So actually, if you rewind the video, you'll see that I almost drew that, and then
Yeah.
oh no, I cannot draw
Okay.
that, and I went over here.
Okay.
Okay, so we're gonna do something very high tech today, which is that I'm gonna actually rotate the camera and show you a picture that I drew over here.
You're gonna see this?
What?
Colonialism?
No, no, no.
Oh.
I mean, if you want, we can rotate the camera 360 degrees, and you can 180 degrees, and you can all wait. But really, I was just trying to get this picture in here. So here's a graph. Okay, this is the complete graph K7, and now I wanna orient it in such a way that it's Eulerian. Okay, and I claim that I can do that by taking the first 3 edges out of each vertex and pointing them out.
Can you repeat the claim?
So I'm just orienting the first, now from clockwise, the first 3 edges go out and the other 3 go in. Okay? So I just drew some arrows and you'll see that actually each edge has been uniquely oriented now. Okay? And so this is,
See this one. Vertex.
huh? Oh,
The seventh.
What did you say you're trying to do? You're trying to show us.
so I claim that this is an orientation where the in degree equals the out degree at each vertex, right? Because at each vertex I have 3 in, 3 out. Okay? And so now I want to walk around this guy, and I know that I can do it because of this condition, but I want to plan it a little bit better. Okay? And I want to plan it by using an oriented spanning tree. Okay? So let me draw an oriented spanning tree. Oh, but well, before I do that, I have to tell you which one is B, which one is E, right? Of course, it doesn't matter too much because this is perfectly symmetric, but let's say that this is B and this is E. Okay? Okay, now I'm gonna choose a spanning tree rooted at B. Okay? And there's many ways of doing it, and I'm just gonna draw one that I prepared ahead of time. And you should check it and make sure that you agree that this is rooted at B. See if you can actually see this in the camera. Yeah. Okay. Okay, so this is my spanning tree T. It's an oriented spanning tree rooted at B. So that accounts for this. And now at each vertex, I'm going to look at the out degree I minus 1 things that I have not used, and I'm going to choose a permutation. Okay. So, I don't know, here, I haven't used these 2 edges, so I choose a permutation of them. Let's say this goes first and this goes second. Here I haven't used these 2 edges, so maybe this goes first, this goes second. Here I haven't used these 2, so this goes first, this goes second. Here I haven't used these 2, so first, second. Here I haven't used these 2, first, second. Here I haven't used these 2, so first and second. Now here's a little bit different because all 3 of them I have not used. Okay. But there's one that's different, which is E. And so I'm going to number the other ones first and second. And I do this arbitrarily. So how many ways are there of doing what I've done so far? I chose a tree and I chose a permutation at each vertex. So this is the number of ways of what I just did. Choosing a tree and choosing a labeling like this of all the out edges. And so from this information, I'm going to perform a walk, a closed walk. Right? That's what I should do, right? I should get a closed walk that starts at E. So closed walk. So what should I do? Well, start at E, right? I should definitely do that. I need to start at E. And then what should I do? What I'm going to do is, whenever I enter a vertex, when I enter a vertex, exit through the lowest number. Okay? And if all the numbers are taken, then take the edge from T. If all are taken, then exit through T. Okay? Actually, there is a comment that I should make about this, which is that, let's say that I stand at a vertex. Right? There's something I'm implicitly assuming here. I stand at this vertex. You see, at each vertex, I knew that my spanning tree had exactly one edge that I used and not the other ones. Why is that? Well, because if you have two of these edges, then that's not directed, right? Because we would have two edges that are pointing in different directions. And if you had none of them, then this guy would be disconnected from the rest of the tree, right? Because all I just point to V. So if I start here, I must be able to point to V somehow. So my tree T has to use one of these out edges. That's why there's exactly one blue edge coming out of each vertex. Okay? And so I claim that with these instructions, I'm going to get an Eulerian path, or an Eulerian cycle. Okay? And again, this is what I have to do this in front of you guys. I'm a little bit nervous, but I think it's going to work out. So let's start. I go. Maybe I'll wiggle so you can actually see it in the camera. So I start with E. Now I get here, and I choose the lowest number. So I take 1, and I get here, and I take the lowest number, which is 1. I get here, and I take 1. I get here, and now I cannot take 1 because that's taken, so I have to go to 2. I get here, and I take 1, which is still available. Then I get here, and 1 is taken, so I take 2. Here, I use 1. Here, 1 is taken, so I use 2. Then I take 1. From here, I can take 1. From here, I can take 2. Now here, 1 is taken, 2 is taken, so I'm forced to use the blue edge. The one from the tree. Now 1 is taken, 2 is not taken, so I go here. Then 1 is taken, 2 is taken, so I take the tree. Here 2 is not taken, so I can take 2. 1 is taken, 2 is taken, I take the tree.
The tree is to the root.
2.
So yeah, go to one
Yeah,
when
yeah.
you lead from.
Did I do something wrong?
No,
Keep
no,
going.
go to V.
Yeah, more stuff. Yeah.
Yeah,
Take
that's it.
two.
But there's 2 edges.
I did do something wrong.
Yeah, and you have to take 2.
Wait.
Yeah, there's two edges.
Oh, no, I'm not,
Yeah.
no,
Yeah.
it's okay.
Yeah.
See, I'm nervous. Right, this is fine, right? I come here, but I don't stop, I continue.
Yeah, keep going.
Because now I say 1 is taken, 2 is not taken, so I can take it, okay? Now here, I go over here, and I go over here. I'm done. It's pretty cool, huh? It's pretty cool, it always works. Actually, that looks pretty cool. So claim this is a closed walk. So why is it a closed walk? Let's see, should I?
Does it matter that it's a complete graph?
I'm sorry?
It's complete. The graph is complete, right?
So it doesn't matter. This works for any graph that's Eulerian, that satisfies these conditions. Okay. Why did this work? Maybe we'll just hand wave for a moment again. So first of all, how could I possibly get stuck? Well, by the same argument as before, you can only get stuck at V. And that's why I got nervous, because I thought I was stuck at V, right? That's why I got here. I was like, oh, I don't want to go to V because that's the place where I can get stuck. If you start at V, you can only get stuck at V, right? And so when you do this, when you run this algorithm, something happens, you walk, and you end at V. You know that, okay? Now the question is, did you hit everybody or not, right? So how do you know that you hit everybody? The reason that you know you hit everybody is the following. Again, maybe I'll pay very close attention because I'm not going to write anything. Suppose that I didn't hit everybody. That means that there's some edge that I didn't hit. Okay, imagine this edge I didn't hit. Now, let's go to the starting point of that edge. So if I didn't hit this edge, and this edge has a number, that means that I also didn't hit the blue edge that was supposed to come after it, right? The one on the spanning tree. So that means that one of the edges in the spanning tree I didn't hit. Okay. Now, let's say that you didn't hit an edge of the spanning tree. Now, the thing is that you did end at V. You got stuck at V, right? So V doesn't have any more exits, which means that you hit all the edges that go into V. So if you didn't hit some edge over here, but you did hit every edge that goes into V, there must be some place where there's an edge in the tree that you didn't use and an edge of the tree that you did use. Okay? But that doesn't make any sense because if you didn't use this edge of the tree, then you didn't use all the in degree of this vertex, which means that you had no business using the last edge coming out of it, the blue edge coming out of it. Okay? So that's an argument for why if you got stuck, then you're finished. And it might be worth for you pausing and rewinding the video if you have that capability and slowing me down. But that's the argument for why this really does produce a closed Eulerian book. Okay? And now to prove this equality, I need to prove the converse. So what does the converse look like? The converse says that if you start with an Eulerian walk, okay? So you just walked around. And now pay attention to the last time that you exited each vertex. So for each vertex, draw in blue the last edge that you exited in that walk. The claim is that that's a spanning tree. That's an oriented spanning tree. And if that's the case, then this is a bijection. Again, it's worth. So I wrote this down. It's worth you looking at it there. But this basically shows that this is a bijection between the left-hand side and the right-hand side, okay. Which is pretty cool. So this means that enumerating spanning trees is not only good for its own sake. It actually allows you to count, the number of ways of walking around a graph. Actually, Stanley has a nice example in the book where he looks at a 3x3 grid, pretends that it's a city, and you have to imagine that you're delivering the mail in that city. And so that means that you have to walk around every street because you have to hit every house, and you have to hit every house in this direction and in this direction. So you actually have to do an Eulerian tour of the 3x3 grid. Right? So the question is, how many times can the delivery person do this without having to repeat paths? And the answer is many, many hundreds of years, if not more, I forget. These are the kinds of things that you can answer. Okay. Now, the thing is that I wanted to write this to motivate a matrix tree theorem for digraphs. Because we had a matrix tree theorem for graphs that are not oriented. But now we want not the spanning trees of G, but we want the spanning trees that are oriented and rooted at a vertex. Okay. So now, instead of this, let me say that G is a directed graph. And now we want to count the oriented spanning trees of G rooted at B. Okay? We'll review some vertex. And it turns out that the theorem is exactly the same. You just have to change the definition of the Laplacian. And it's very easy to change it. The Laplacian, what you're going to do to the Laplacian is just now the ij entry of the Laplacian is going to be the number of arrows from I to j. Okay? So this matrix is no longer symmetric. You might have edges from I to j and not from j to I. And now, instead of the degree of I, you have to put the out degree of I. And if there are any loops like this, then you should remove them. Okay. So you just change the Laplacian very slightly. And the claim is that when you do that, then this Laplacian enumerates the trees for this directed situation. Okay. And the proof is basically the same. And in particular, one thing that this shows, and this also shows, is that this quantity, okay, this is the same tau of d comma v. This quantity does not depend on v. And you should find that surprising, actually. This is clear, but this is much less clear. This is independent of v.
Is that because the oriented spanning trees can look very different depending where it's rooted?
Yeah, that's right. So if you there's in a graph the trees rooted at one vertex probably look very different from the trees rooted at a different vertex, but they're in bijection. So I just erased the statement of the theorem, but anyway, just to give you an example of an application of this. If our graph is the complete graph directed, so between every two edges you have edges in both directions. How many Eulerian cycles do you have? And like I said, it doesn't really matter where you start, the number is the same. So what's the number of Eulerian walks? Well, it's the number of spanning trees, right? Which, the number of directed spanning trees here, it's very easy to see that a rooted spanning tree here is in bijection with a normal spanning tree without an orientation. The number of spanning trees is still n to the n minus 2. And now I'm supposed to multiply by out degree minus 1 factorial for all the vertices. So what is the out degree of each vertex here? It's n minus 1. This is the complete graph Kn. So every vertex is connected to the other n minus 1 of them. So I take that out degree, I subtract 1 from it, and I take that factorial. And I'm supposed to do that for every vertex. And that's it. This is the number of ways of walking around the complete graph, hitting every edge exactly once. Very nice, simple, clean formula. So this is just scratching the surface of this theory, but this is how it starts, and these are some of the first nice, interesting examples.
What's the theory goal?
It looks like it's time to go, but I mean, this is just if you look for like matrix tree theorem and Kirchhoff's theorem and like I said, this is currently, it's a very active area of research to extend this to higher dimensions and see what higher dimensional matrix tree theorem looks like. Or I put a project on the list about matroid matrix tree theorems. There's a lot of stuff related to this, and this is all or at least most of this is in Stanley's book, and there's lots of references there also, and I can point you to other things. But it's like we have to go, so let's stop there.